Let's talk about the concept of absolute versus conditional convergence. What we're saying is that if the absolute value of our series converges, so if we take the absolute values of all our terms and sum them up, if that converges, then our series as it is converges absolutely. It doesn't matter if our series alternates, if it's always positive or always negative. If we take the absolute value and that converges, then our series absolutely converges. On the other hand, if our series converges, but the absolute values of the terms, if we sum those up, that diverges, then what we get is something called conditional convergence. Our series conditionally converges. So a lot of times you'll get a question that asks, show if this series converges conditionally, absolutely, or diverges. So when we get a question like that, we got to follow a couple steps. The first thing you do is you want to check if the series, if the absolute values of the terms, if we sum those up, if it converges. If we go back here, if it converges, well, that tells us that our series converges absolutely, and that's it, we're done. If it doesn't, then we check for conditional convergence. And for conditional convergence to occur, we have to meet these three rules, which is the first thing is that our series strictly alternates. This means that every term switches signs, so we're adding a positive, then a negative, then a positive, then a negative. The next thing is that the limit of as n approaches infinity of our a sub n is equal to 0. That's pretty much the nth term test. And lastly, our series has to be decreasing. And now let's just look at a sample, a quick one, and we're going to go ahead and use the alternating harmonic. So the harmonic, as you guys all know, is the sum, and we'll start it from n equals 1 to infinity, of 1 over n. And the alternating harmonic is simply this, the negative 1 to the n. So, the first thing we do, let's remember, is we check if the absolute value converges. Well, you guys should already know that, well, if we just take the absolute value, we're getting rid of this negative 1 to the n. So the absolute value that's just equal to the harmonic, which diverges. So right there, we can say that it doesn't show absolute convergence. So let's look at our list. Well, it didn't converge, so now we got to check for conditional convergence. So our first thing it needs to pass is that it strictly alternates. And strictly alternating, you can show that in a couple ways, and the most common way you'll see it is the way you see it in this problem, which is negative 1 to the n. So yes, it strictly alternates. Another way you could see it is sine to the pi n, because sine will switch sign every pi. And then our second rule is limit as n approaches infinity of a sub n, that needs to equal 0. And if we take the limit as n approaches infinity of a sub n, and this should actually, we're looking at the absolute value whenever we're doing conditional convergence. Well, that's just the limit as n approaches infinity of 1 over n, which equals 1 over infinity, which is 0. So yes, that passes. And the last thing is that our a sub n need to be decreasing. And to do that, we rewrite a sub n as a function. So we'll write it, instead of 1 over n, we'll write that as 1 over x, and we'll set that equal to f of x. And to say that it decreases, well, we know how to do that. We just take a derivative, and we want to see it be negative. Well, the derivative of 1 over x, that's the same as x to the negative 1, so we get negative x to negative 2. And that's always going to be negative. So, yes, it decreases. Since it met all these three conditions, our series conditionally converges. Conditionally, yeah. And that's it.